Hi, I'm Ben-Yaakov. The title of this presentation is The Voltage Multiplier and How It Should Be Named. The presentation will cover the operation of the voltage multiplier, and then I'll dwell a little bit on the history of how it was actually developed. The purpose of the voltage multiplier is to generate a high voltage from a lower voltage. The excitation is a AC source, and then we have a series of capacitors and diodes, and eventually we end up with the output voltage. Now shown here are actually three schematics. This is the same circuit, only people have been drawing it in different ways, so I thought I'll put it in a different configuration, but of course it's the same circuit. Now, the purpose here is to generate a high voltage, which could be useful in many applications, ranging from X-ray machines to flash lamps and many other applications. You start with a low voltage. This is an AC source, and then you sort of build up the voltage until you get a high voltage at the output. Be here, here of course. Now, the multiplier could have a filter capacitor at the output or a hold-up capacitor at the output, or not, depending on the application, and then RL actually represent the load. So let's see how the voltage is being built up in this ladder type circuit. I'll start off assuming that from zero condition, there's no voltages on the capacitors, and also assume that there is a voltage source, a square wave, which will be easier to analyze, with a peak voltage or maximum voltage of plus V in and minus V in, plus minus at a certain frequency. Let me start off with a negative voltage. That is that V in now here is negative. That is that the polarity is like this. Now, as you'll see, the path now is open. The diode can conduct because there is a positive voltage here, and being a square wave, and if there is sufficient time, this capacitor C6 will be charged this way to V in, to the voltage of this source. Okay, now we move to the next cycle, or the next half cycle I should say, in which the voltage is positive, that is plus V in. In this case, the polarity is reversed. Let me just put it here, like this is plus and this is minus here. And as you can see, from ground to this point I have two V in. Okay, so the V in of the source plus V in of the capacitor, and therefore there is a positive voltage. This capacitor C5 is still with zero voltage on it, so it'll be now charged this way to the total voltage, which is 2 V in. And in fact, the voltage of this point to ground will be 2 V in. Okay, so we have now two capacitors charged. So we move now to the next half cycle, that is the negative cycle, where here we have minus V in. So the polarity is again like this. This is plus here and minus here. And notice that since now this capacitor C sub 6, this capacitor here, is charged, the voltage from this point to ground is zero, because we have plus and minus. So C4 now has a zero voltage at this point with respect to ground. On the other hand, we have from here, from ground, to this capacitor, 2 V in. So through this diode now, C4 will be charged to twice V in. Okay? So now we have actually charged C4, and I'm not going to continue. As you would understand, on the next cycle we'll charge C3 to 2 V in, and then C2 to 2 V in, and eventually to C1 to 2 V in. So from ground to the output, in this particular case, in which we have 3 stages, 6 capacitors, we have 3 times 2 V in of this capacitor, this, and this, the sum of which is 6 times V in, or twice the number of stages. M is the number of stages, or if you want, N times V in, where N is the number of capacitors, because each stage is built with 2 capacitors. Now, in the steady state, current will be drawn here, and the circuit goes on pumping charge to the capacitor, which are draining the charge to the load. Now, we can now have a sort of a different look at what is really happening here by watching sort of the operations that go on in the the positive half cycle and negative half cycle. Let me start off with the positive half cycle. In this case, we have the polarity of the source on this way, and therefore the voltage at this point is twice V in. This capacitor is charged to V in, but meanwhile it's sort of discharged a little bit because charge is being drawn to the output. So now, since we have now the source here, so we have a sort of a higher voltage than the voltage of the capacitor, the charge is replenished by the source. Okay, so C5 is now getting to be a higher voltage. Same goes with C3, because this voltage is becoming higher, this point here, so therefore this one is also higher, as well as this one is going a little bit higher. So this is charging this one, and this is charging this one. So we are kind of making up for the charge that was drawn to the output. So let's move now to the next half cycle, in which the excitation, the source, is negative, minus V in. Now, C6, that previously was sort of partially discharged, can now be charged again by the source. Same goes for C4. C4 was delivering charge to C3, and now we can, since C5 is now fresh, we can have the charge coming to C4, and so on and so forth. And by this, we actually connect one series of capacitor one half cycle, and then the other one at the next half cycle, and by this, we sort of move the charge from the source up, and eventually to the output. This is really what happened. Now, the excitation of the voltage multiplier could be either by a voltage source. Now, we've seen earlier the square wave, but it could be also a sinusoidal wave. In fact, this is the more common way of doing it. In this case, the capacitor will be charged actually to the peak voltage, right? Because when the input voltage is low, the diode will not be conducting. A better way is to use a current source. Here's a current source which is sort of pushing current through the capacitor. In this case, current will be moved either this way or then the other way. The operation is very, very similar, except that now the excitation is a current source rather than charging the capacitor with a voltage source. Now the difference between the two is really in the way the current is flowing. In the case of, say, a square wave, what we are going to see here is typically the capacitor voltage is going down because it's discharging, and then the excitation comes on, and at this point the capacitor is being recharged again, and you'll have a spike of a current. Next cycle you have another spike. That's not very nice, because this means high current stress. It means noise, interferences, and if it's high frequency, it may be a little bit difficult to suppress. However, if the source is a current source, the story is entirely different. We are forcing a current, say in this first negative half cycle, we are forcing current through a capacitor. This will be the same for the other capacitors, and therefore the current will have the shape of the source. If it's a sinusoidal source, it will be a sinusoidal wave shape. So that as soon as the current starting to flow, capacitor will charge up to the point that the current is stopping, and then of course, because of the diode, there's no negative current, and the next half cycle, the capacitor will discharge because it will be delivering the charge to the corresponding capacitor. So a current source is really a neater way, except that it usually requires extra electronics circuitry, because we don't have natural voltage sources. The next question is, how do we choose the capacitors for a given application? Okay, now these two equations are for the case that there is no output capacitor, and we are talking about the steady state, or maybe with a capacitor, but the steady state situation. Now, IL is the load current. That is how much current do we use and deliver to the load. N is the number of stages. That is half the number of capacitors. F is the switching frequency, and C is the size or the capacitance of the capacitor, assuming that all capacitors are of the same capacitance. So this equation says that if you load here's the structure, and you load it with a certain I load, you will have a voltage drop. That is, you will not get N stages times V in. This will not be the case. You will get a lower voltage, actually a delta V, and this is the expression for the delta V. So as you can see, the larger the number of stages, the larger will be this delta V. And the larger the capacitor here, the smaller will be delta V. That is, large capacitor will maintain a higher voltage. So one has to decide now what is the acceptable delta V in a particular application. Knowing the switching frequency, the load, you can calculate what will be the capacitance of the capacitors that you are going to use. Another question is the ripple. Now, the output voltage will have some ripple because the operation of the circuit is such that you are delivering sort of a fixed amount of charge each time, and therefore the voltage will go up and down. This is the output voltage, and here is the ripple. This is this delta volt peak to peak, and this is the expression for this ripple. Again, it's a function of the load, because if the load is higher, then of course it'll go deeper. It's a function of the capacitor. A big capacitor will maintain a constant voltage, and it is a function of the number of stages that you have. So you can use these two equations, which have been developed or derived by many people in many papers, and use them in order to choose your operating condition. Let me move now to a somewhat different area, and that is to the question, how was this circuit, the voltage multiplier, developed? Now, the circuit was described in a paper published in 1932 by Cockcroft and Walton. Cockcroft and Walton are associated with this circuit. In fact, usually this circuit is referred to as the Cockcroft-Walton voltage multiplier. And this is the way it is usually recognized. Cockcroft and Walton worked at the laboratory of Lord Rutherford, who was a renowned scientist working on elementary particles, and he needed high voltage in order to accelerate the ions. And they actually developed the circuit for this purpose. And indeed, in the paper, you can see that they described exactly the voltage multiplier. This is the load, in fact. Here are the capacitor. These are actually vacuum tube, at the time, diodes. Well, I guess they forgot to put the excitation, so it was put the last minute. This is the excitation. This is the AC source. This actually explains how the circuit works, and indeed, they aimed at 1 million volt total output voltage. Now, obviously, the initial voltage was very high itself, but nonetheless, the target was million volt, and they got pretty close to it. And indeed, they got up to 700 kilovolts with the circuit that they have built. Here is the original picture from the paper. In the paper, they have actually printed this picture of their lab. We'll see in a minute what all these balls mean. I guess there's a covered part here. I guess there's some secrets they didn't want people to know about. And here is a construction of the voltage multiplier that was used, by the way, in many physics laboratories and by many researchers. This is also for extremely high voltage. These are the diodes here. These are, again, diodes of high voltage because you end up with hundreds of kilovolts. These are here the capacitors. So this is basically sort of a physical realization of the circuit that we have seen. However, in 1920, Greinacher, a Swiss-German scientist, published a paper in German, and this is the Google translation of it, which described a circuit that includes valves, this is diodes, and condensers for high voltage generation. And lo and behold, this is exactly the same circuit. Here are the capacitors. This is actually the diodes. At the time, there were no diodes, and he had to actually to fabricate the diodes in his own lab, but the circuit is the same. This is the excitation in here. And as you can see, here is the capacitor, and eventually we got the high voltage coming out from here. He, in fact, got a patent on 1919, and Crockford and Walton also got a patent about 10 years later. And apparently neither them nor the patent office in England knew about the fact that not only did he publish this paper, but he actually got a patent on it. Now, Greinacher is really not very known. People are not aware of this remarkable scientist, but he is the one who actually invented the magnetron. This is the heart of the microwave oven that is now produced and found in every kitchen now, worldwide. Probably millions of them are around. And he is the one that actually invented this in 1920, around 1920. That's really remarkable. So the question is, how should we name this voltage multiplier? Well, a key point is whether Cockcroft and Walton knew about the circuit that Greinacher invented. Probably not. He published it in an obscure publication in Germany, I guess, and nobody really knew about it. And so that they have, I guess, reinvented it. And also it should be said that if they would not have published the papers, somebody along the line, maybe some years later, would have reinvented it, because people have been looking for high voltage circuitry. However, the achievements of Greinacher are really remarkable. At that time, 1920, the technology was very, very primitive, and devices that he had sort of to build his own things. So I would pick him as I would choose to name the multiplier after him, but of course it's a matter of choice. So this brings me to the end of this presentation. I hope you enjoyed it and you'll find it useful, and thank you for your attention.